Hey everyone, it's Miss Baz. Today we're talking about Unit 3, Sections 3.4 through 3.6 so that we can look at the properties of gases. So let's get into it. First, we're going to start with topic 3.4, the ideal gas law. By the end of this, you should be able to explain the relationship between the macroscopic properties of a sample of a gas or mixture of gases using the ideal gas law. So this is the equation sheet that we typically use in our class. This is the one that helps us to navigate all of the information we need to know. So what we're going to end up doing with this is making sure that by the end of this, we know this sheet really well. We know where to find everything. There's conversion factors on here. There's all kinds of stuff. But what we really want to focus on in this moment is this bottom half of the sheet. All right. So this is the bottom half of the sheet. This is where we're really going to focus whenever we're looking at the properties of gases. So there's a couple of gas laws we want to look into. The first is Boyle's law. So Boyle looked at pressure versus volume. And what he found is that they have an indirect relationship. All right, so I'm going to move myself so that you guys can see this better. All right, so this is actually called the graphical and particle view. All right, I want to make sure you have all the views so that you can see it. So here's what's key: pressure and volume. Sorry, I like mine's this way. I'm going to use this tip of my pen to represent volume and this flat end to represent pressure. Okay, so what he literally found is that as my pressure increases, my volume decreases. Okay, vice versa. If my volume increases, my pressure decreases. So literally they have an inverse relationship. They affect each other in the opposite directions. And the way that our graphical and particle view shows this is that as you go across the graph, sorry guys, as you go across the graph, you'll notice that as literally the pressure literally is going, so like at the top, that's where we have the least amount of pressure, right? And the volume, this is where the changes are happening. So you want to pay attention. Sorry, least the 0, 0, right? Least amount of pressure. So you want to pay attention to this graph. It's showing us how that change is happening. Okay. So Charles' law, because you need to know the graphs. Charles' law, volume and temperature. So what he did, right, is he looked at volume and temperature. So he already saw about pressure was looked at, and he said, okay, well, what about temperature? How does that change it? So what he found is that as you increase your temperature, your volume increases. So if this is temperature in the middle, right? Boom. If I push the middle up, the end goes up. Makes sense? All right. And if you notice, pressure still decreased as my volume increased. So they have a direct relationship. They affect each other directly. Temperature and volume, direct relationship. Okay. So something else to pay attention to with both of these equations. You'll notice that the two things that are right next to each other affect each other oppositely. The thing on the top versus the thing on the bottom, they go in the same direction. Okay, really important to notice. And you can see from that straight line on our graph that that's true, right? It's a linear graph. So Avogadro, which, right, the mole, he helped us with our amounts. He looked at the volume versus the amount. So what he said is as the number of moles increases, the volume increases. So same thing, if we look right here in the center, if we treat our amount like our temperature, it's in the center. As this increases, boom, right? Direct relationship. All right. And that's a picture of it. This is another picture. If we saw a graph, the graph would look exactly like the Charles law graph. Okay. Now, Gay-Lussac, the pressure versus temperature, direct relationship. Again, temperature's here, pressure's here. As my temperature increases, my pressure increases. Okay. As pressure increases, temperature goes up. We can see that on our graph here. Now, these two graphs comparatively, just so you know, this one is what it looks like with temperature. This is what it looks like with volume, okay? So keep that in mind when you're thinking about it and looking at the graph, okay? So here's our equation sheet. Remember, we're focused on the bottom half. So if you look right here next to me on our graph, you'll see this beautiful law right here. This equation is the combined gas law equation. Okay, so as you notice, this equation features all of our parts, right? Except N, but all you do is switch T with N, you got it, right? All right, here's something else to think about, the ideal gas law. So remember that all the gas laws have a constant, okay? All gas laws have a constant. If all of these constants are combined, you get a new constant called the universal gas constant, okay? A gas law can be written that allows the values of a single gas to be calculated if the characteristics of that gas are known. So what that literally means is that I can tell you how much of a singular gas there is. I can tell you the temperature. I can tell you the volume. I can tell you the pressure. I can tell you any of those things if I know at least three, right? Of the other ones. So here's my gas constant. My gas constant R, there's two possibilities. There's R equals 8.314 joules per mole per Kelvin. I would use that if joules or another unit that can be converted to joules is being used, okay? The bottom one, 0.08206 liters per ATM per Kelvin per mole. That's the one we're probably going to use most often that right now. That particular one, right? Liters we know as volumes. ATM is a pressure unit. Kelvin is a temperature unit. Moles is our amount. Here's what's really important. You must use those units in the equation. So if any of the numbers you're given are not in those units, you have to convert them. Okay? The ideal gas law is expressed as P times V equals N times R times T. Okay? Which makes sense because if you rearrange it, right, we can divide P and V by N and T to get R. Makes sense, okay? All right. This is the most commonly used gas law. Any of them can be calculated if the other three are known, okay? So the ideal gas law can be used to calculate the molar mass of gas if the density is known. Remember that density is equal to mass divided by volume, DMV, okay? Which unit-wise is grams per liter. We can combine grams per liter and the Pivnert ideal gas law to solve for molar mass. Mass is equal to grams per mole, right? So when we find the molar mass of something, we're like, it's this many grams per mole, all right? The equation to the right is not on your equation sheet, but here's why it's important and why you want to know it. Molar mass, cat puts dirt over P. What you're literally going to do is where you have moles in the equation, you can plug it in as mass over the molar mass, okay, which is equal to density. All right, so an easier way to think of that is if I take the grams they give me and the volume they give me, mass divided by volume is density. Instead of N in that equation, I put D in there and I also leave the V out, right, because I already used it. So you plug all those things in, you get your mass that you're looking for, okay? So it takes practice and being able to recognize it, but it's an important equation, okay? Molar mass, cat puts dirt over P. All right, I'm going to move myself to the right. So Dalton's law of partial pressures explains that the total pressure of a mixture of gases is equal to the sum of the pressures caused by the component gases. So literally what that means is the total pressure of a mixture of gases all combined together in whatever container I have is the total, it's the sum. Each individual gas has its own pressure, okay? So this is best expressed as P total equals P A plus PB plus PC and so on and so forth, however many gases you have in there. So each of the pressures of the individual gases is called partial pressure. Okay, so for example, if I had an oxygen gas, a nitrogen gas, and a chlorine gas all in the same container, then I can literally get each individual pressure, right? And I have the total pressure, okay? So that's partial pressure. So the way I can find this, the partial pressure, is by using the mole fraction. So the mole fraction is the ratio of any, the amount of the component versus the total amount. So if I know I have a certain number of moles of a gas, I take just the moles of that specific gas and divide it by the total moles to find that gas's partial pressure. Okay. So what should you be able to do with this? Examine the graphs of P, V, T, and N to determine the relationship. Use the ideal gas law to calculate the conditions of a gas. Given the initial and final conditions for 2 or 3 properties, qualitatively or quantitatively, determine the value for an unknown condition. Apply the concept of mole fraction to determine the partial pressure of a gas present in any mixture. Calculate the density of a gas given its identity, temperature, and pressure. Okay. So this is the end of 3.4. I'm going into 3.5. 3.5 is kinetic molecular theory. So this is used to explain the relationship between the motion of particles and the macroscopic properties of gases with the kinetic molecular theory, a particulate model, and a graphical representation. Okay, so here are some characteristics of gases that hopefully we already know from when we took chemistry before. They're widely spaced particles. They're always moving. They flow readily, right? So they easily move. They take the shape and the volume of the container they're in, and they're easily compressed. I apologize. Most molecular substances of low molecular weight are gases or easily vaporized liquids at room temperature. Another word for gas is vapor. This word is often used in conjunction with the word volatile, which means easily vaporized. Sorry, guys. All right. When we think about the word volatile, a lot of times we think dangerous. So instead of dangerous, it literally just means that it's easily turned into a liquid, which can make it dangerous. But that's really what it's about. Volatile means easily turned from a liquid to a vapor. Okay. So assumptions of kinetic molecular theory. So this is KMT, kinetic molecular theory, that you should be able to explain. All right, gases are made of molecules or atoms in constant random straight line motion. The particles fill the container. The volume of the particles is negligible, meaning does not matter. The pressure in the container is caused by the collisions of particles with the walls of the container. Particles in a gas do not exert forces on each other. Okay, each molecules act independently and all collisions are elastic. Basically, kinetic molecular theory is making these assumptions, and then the average kinetic energy movement is directly proportional to the Kelvin temperature. So kinetic molecular theory is taking what we already understand about gases and then adding some words to it, right? So it's saying they're made of molecules or atoms in constant random straight line motion. So the molecules are literally straight lines, okay, all the time. The particles take up the whole container. The volume does not matter. Okay, that's what negligible means. So these are assumptions. Remember, assume. Okay, the volume of the container doesn't matter. The pressure is strictly caused by the collisions of the particles with the walls of the container. So basically the idea that like every time one of the particles hits the wall, that's what creates the pressure. All right. And then particles in gas do not exert forces on each other. Each molecule acts independently and all collisions are elastic. That's the assumption that there are no intermolecular forces. Okay. So like literally elastic just means like it never stops its motion, right? It doesn't absorb it doesn't slow down in any way. It doesn't speed up in any way. It's just the exact same motion. All right. And then the average kinetic movement is directly proportional to the Kelvin temperature. So that literally means that the kinetic energy directly proportional, meaning like as the Kelvin goes up, the energy goes up, right? So here's a picture kind of showing a little bit more of that thought process. And I want you to pay attention and see if you notice anything about some of these molecules. Like you see how like that, so like for example, this one is moving super slow. Even when another one hit it, it didn't change its speed. It didn't change, like it keeps going, okay? That's the idea, is that it keeps maintains, okay? None of these are changing, it stays the same. That's the idea, okay? All right, now here's another thing to think about. The Maxwell-Boltzmann distribution, okay, says that the kinetic molecular theory can be applied in conjunction with velocity to describe the movement of gases. The relationship evident in the distribution is pictured as the heavier the gas, the lower the speed. Okay, so what that literally means is that as the gas gets heavier, it moves slower. So the further down a group I go, the slower the gas, right? All right. So remember that according to the KMT, the average translational kinetic energy of a molecules of a gas is directly proportional to the Kelvin temperature. So for different gases at the same temperature, the factor that would be changing the speed is the molar mass. This is evident when we look at the kinetic energy equation, which is what they were showing us on the slide before. Okay. That if we take half of our mass and we multiply that by our velocity squared, we should be able to get what the kinetic energy is, the actual movement um, of that molecule. So you should be able to draw a representation of gases under given initial or final conditions for pressure, volume, temperature, and amount. You should be able to apply the kinetic energy equation to compare the velocity of different gases. And you should be able to look at the distribution, that graph of known and unknown gases to be able to identify what the unknown is. Okay. The last thing we want to talk about with this section is the deviation from the ideal gas law. So basically how real gases behave, okay? So a real gas versus an ideal gas. Gases that follow the kinetic molecular theory guidelines are called ideal gases. Gases that do not adhere closely to these properties are called real gases. Real gases don't do ideal behavior, okay? Real gases don't do the ideal thing. Okay, so low temperature, high pressure is what's behind me. High temperature, low pressure is what's next to it, right? So here's what's true. This is why this is in this picture. Okay. Ideal gases or real gases deviate from ideal behavior under conditions of, if there's low temperature, there's actually less kinetic energy because there are intermolecular forces at play, right? If there's a higher pressure, the particles are super close together, okay? The particle volume is significant relative to the overall size and more likely to have London dispersion forces. So under these conditions, there are two major differences between real and ideal gases. Calculated pressure is going to be usually too high because, people are assuming the KMT is assuming all kinetic energy goes into the collisions with the walls. But the truth is that intermolecular forces are actually slowing them down. And then usually the pressure for a real gas is lower than whatever you've predicted. Another thing that's happening that could happen is the calculated volume can be too large because you may assume that gas particles have no volume, but they do. Okay. They take up space. Okay. So standard temperature and pressure, right, is 273.15 Kelvin and 1 atm. You want to make sure you know these conversion factors. You're going to use standard temperature and pressure most often to help us with our real gases and our calculations, okay? So this is a chart that explains the differences between the two. Make sure you spend some time, pause, look over this, make sure you understand the differences, can explain them. And then that is the end of this section.